Hello viewers, welcome back to Nature Academy. This is Dr. Shaik Ahmed. In this lecture, we are going to discuss the fourth postulate of quantum mechanics. The fourth postulate of quantum mechanics deals with the probabilistic outcome and expectation value of an operator. The contents of this lecture are listed here. The first one is the probabilistic outcome of measurement, second one expectation value, Heisenberg uncertainty principle, compatible operators, and followed by some solutions to previous questions. So in this lecture I am going to discuss briefly what is the fourth postulates of quantum mechanics, and I also discuss the expectation value of an operator and the Heisenberg uncertainty principle. So first of all, I'll start with the fourth postulate of quantum mechanics. The fourth postulate of quantum mechanics deals with the probabilistic outcome of measurements. Before moving to the fourth postulate, I want to recall all the three postulates which we discussed in the previous videos. The first postulate of quantum mechanics, so this is first postulate of quantum mechanics. It describes the state of the system, and the state of the system is represented with a wave function. This wave function contains all the information of the system. So if you know wave function, we can calculate we can determine many physical properties of that system. So the wave function is used to describe all the information of the system. That is first postulate. And the second postulate it deals with the observables and corresponding operators. So second postulate is used to describe the operator mechanism. That means if you take any observable, any measurable physical quantity, for example, let's say position, the position can be represented with an position operator, and the momentum is a physically measurable quantity, then I can associate an operator with this one. So the second postulate deals with the operators. So if you want to define an operator, if the operator is acting on a state function, then the state function may changes to some other form. Let me call this a psi prime, okay, of the same vector space. Psi and psi prime belongs to same vector space. So operator A is nothing but it's a mathematical formula or mathematical rule which changes one wave vector, one state vector to another state vector. So this is about the operator mechanism. And the third postulate deals with the eigenvalues of an system. What is eigenvalue? So here I will write an eigenvalue equation. When an operator is operating on a wave function, that means we are doing some measurement here. So we will get a result of that measurement, and that result is known as an, and the wave vector will be psi n. So here the operator A is acting on a wave function psi of n, then you will get same wave function psi of n, and with a coefficient. Here the coefficient is known as eigenvalue. So each and every measurement gives you an eigenvalue. This is known as eigenvalue equation. These three are the postulates. First, second, third postulate, they deal with the state of the system. The fourth one is the probabilistic outcome of measurements. When measuring an observable A, this observable may be your position, energy, momentum, kinetic energy, anything. If you want to measure an observable A of a system, the system is in a wave function psi, the probability of obtaining one of the non-degenerate eigenvalues of the corresponding operator A is given by. So here I'll write the eigenvalue equation. When an operator is operating on a wave function psi n, you will get like this. You will get eigenvalue equation like this. Operator A is operating on a wave function psi of n, then you will get a result. That result is known as eigenvalue an and the same state function psi n. If the system has different eigenvalues, non-degenerate eigenvalues, that means the eigenvalues are different. They are not equal. Different eigenvalues have different eigenstates. So if your system has non-degenerate eigenvalues, then the probability of obtaining one of the non-degenerate eigenvalue is given by expression. The probability of obtaining one of the non-degenerate eigenvalue an is given by this expression, modulus of psi n psi whole square divided by the normalization constant. So here this psi into psi n is a normalized wave function. It gives you the normalization constant. For example, the system has 4 eigenvalues. Now I want to calculate the probability of getting the second eigenvalue. The probability of getting the second eigenvalue can be written as like this. P2 of A2, the probability of getting second eigenvalue, and this can be written as state psi 2, which has eigenvalue A2, and the wave function psi, and you can write modulus square here, divided by the normalized wave function like this. So this is the probability of getting eigenvalue A2 if different eigenvalues are there, if you have non-degenerate eigenvalues. Yeah. If the eigenvalue is m-fold degenerate, degenerate means the system may have eigenvalues like this A1. So what we thought initially, we thought there are 4 eigenvalues, and these eigenvalues are different. They are not equal to each other. A1, A2, A3 are the different eigenvalues. Then I can call them as non-degenerate eigenvalues. If two eigenvalues are same, so I can call this degenerate eigenvalues. Or in other case, wave functions having same eigenvalues, different wave functions. For example, wave function psi1 is having eigenvalue a1, and psi2 is also having eigenfunction psi2. Psi2 wave function also have same eigenvalue a1. So then I can call a1 is a degenerate eigenvalue, and these two are eigenfunctions. So different states may have same eigenvalue. Such type of eigenvalues are known as degenerate eigenvalues. If we have two eigenvalues, this will be twofold degenerate. If three eigenvalues are same, that will be known as threefold degenerate eigenvalues. If we have eigenvalue an, which is m-fold degenerate, then the probability of obtaining one of the degenerate eigenvalue an can be written as, so you have to write psi n psi modulus whole square, and divided by this one. You should use one summation here, j is equals to 1 to m. By doing some problems, you will get a clear picture. Here is one example, that is this question appeared in GATE 2016. The state of a system is given by psi is equals to phi 1 plus 2 phi 2 plus 3 psi 3 phi 3, where phi 1 phi 2 phi 3 form orthonormal set. The probability of finding the system in the state psi 2 is. So the state of the system is given by wave function psi. In the previous lecture, I mentioned that the wave function need not to be a single wave function. It can be a combination of other wave functions also. So this is given by superposition principle. According to superposition principle, the wave function of a system can be represented by the linear combination of any other states. So you can take two states, psi1, psi2, the sum of two states, or you can also write minus psi3 like this, plus etc, etc. Anything you can write. So in the same way, here the state of system is given by psi is equals to a combination of three other states. So the eigenvalue of psi1 is 1 here, and eigenvalue of psi2 is 2 here, eigenvalue of psi3 is 3 here. These are the coefficients, right? So three non-degenerate eigenvalues, and these wave functions are of orthonormal set. Then the probability of finding the probability of finding the system in the state psi2 is given by. So you know the formula, that is probability of obtaining the system in the state psi2 will be bra vector psi2 and the state vector psi. You should take a modulus square here and divided by the normalization of the wave function psi psi. So if this is the way the eigenvalues are degenerate, then you have to use the summation here. Since the given wave function has non-degenerate eigenvalue, this is the required expression. I'll write here how to calculate psi2 and psi. So since all these psi1, psi2, psi3 form orthonormal set, so I'll write here this is psi1 plus 2 psi2 plus 3, sorry, phi 3. These are 5 values, right? This one 0, and 2 into phi 2 and phi 2, this is orthogonal, this is orthonormal, that means it is 1, and this term also 0. So you will get first term 0 here and second term 0. So when phi 2 is operating on phi 1, you will get 0. When phi 2 is operating on phi 3, it is 0, since they are orthonormal. And when phi 2 is operating on phi 2, you will get 2 here. Take modulus and square it, you will get 4 here. So on the numerator you should get 4. Now what is the normalization constant here? Psi into psi. The normalization constant, I will calculate here. Psi into psi, it will be like bra vector phi 1 plus 2 into bra vector phi 2 plus 3 into bra vector phi 3. So this is one function and you have to apply a psi on it, that is phi 1 plus 2 phi 2 plus 3 phi 3. So when you calculate this one, you will get phi 1 phi 1 is orthonormal, so you will get 1. So as a result I can write this is 1 square plus 2 square plus 3 square. So that is 4 by 1 plus 2, 1 plus 4, 5 plus 9, 14. So the answer is 2 by 7. So the probability of obtaining the probability of obtaining the system in the state psi 2 will be 2 by 7. I hope it is clear to you. So moving on to another problem, this is very important problem. This question appeared many times. This question appeared in CSIR June 2013 and December 2013, JEST 2014, and also it appeared in TIFR exam also. So this question appeared nearly 5 times in various exams, apart from the Central University exams. So what is the question here? In a basis in which the z component of Sz is the spin operator and z axis, an electron is in spin state psi is given here. In a basis in which z component of Sz of the spin is diagonal, an electron is in spin state psi is equals to 1 plus I by root 7 and another element is under root 2 by 3. The probabilities that a measurement of Sz will yield the values h bar by 2 and minus h bar by 2 are respectively. So what he is asking there, the probabilities of measuring h bar by 2. So this is an eigenvalue, the eigenvalue of Sz, and he is also asking what is the probability of obtaining another eigenvalue minus h bar by 2. How will you get your eigenvalues? If we have a matrix, for example say A, B, C, D, this is a 2 by 2 matrix. How to obtain the eigenvalues of this matrix? You should calculate, first of all you should write the characteristics matrix and equate it to 0. The data of the characteristic matrix will be 0. From this you will get two eigenvalues, lambda 1 and lambda 2. So here Sz is given, you know the Sz value, right? What is Sz? This is spin of the matrix. This is simply like h bar by 2, 1 0 0 minus 1. This is Sz matrix. This is Sz matrix, the spin matrix along z axis. So when you find the eigenvalues of this matrix, you will get two eigenvalues. One is h bar by 2 plus h bar by 2 and other one is minus h bar by 2. So for corresponding this eigenvalue, you can also find eigenvector. So the eigenvector will be 1 0, the upspin eigenvector, and this is for downspin eigenvector. So these are the two eigenvectors. So the probability of obtaining eigenvalue plus h bar by 2 can be written as, so this is column vector, right? So this is a column vector or ket vector, and the ket vector when converted into bra vector, when you apply the complex conjugate, you will get 1 0 as the bra vector and this will be row vector. So here the formula is, if I say this is phi 2 and psi, this is modulus square and divided by, this is phi 2 and this is phi 1, then the probability of obtaining plus h bar by 2 will be like this, 1 plus I divided by root 6. Simply you will get this expression. So this is nothing but square root of 1 square plus 1 square, this is modulus and there is a square here, and root 6 whole square is simply 6. So this will become root 2 whole square, and that means 2 by 6 this one. So I can write 1 by 3. So the probability of getting the eigenvalue plus h bar by 2 is 1 by 3. Check the answers here. No need to go for the second one. So if you calculate p of h bar by 2, the first value answer is 1 by 3. So 1 by 2, 2 by 3, 1 by 4 and 1 by 3. So this is your answer. So no need to do the second calculation. So what is the question here? The probabilities that a measurement of SZ will yield the value h bar by 2 and minus h bar by 2. So for h bar by 2 we are getting 1 by 3. For example, if the answer consists of for example option B is also have 1 by 3 and 1 by 3, then you have to check for the second possibility, that is P of minus h bar by 2. I will do that here, but in exam you can skip that one. So minus h bar by 2, the probability of obtaining minus h bar by 2 will be, so this is my second wave function psi2 and modulus square divided by the normalized wave function. So I can write it's an inner product of the two wave functions. Psi2 is what here? That is 0, 1, and the wave function is simply this is 1 plus I by root 6. This is the first element of this matrix, and root 2 by 3, and then there is a modulus square. Denominator it is 1, since this is normalized wave function. You can check the normalizing condition also. So as a result, here you will get root 3 by root 2 square. Since when you do the matrix multiplication, 0 into this term, it will become 0 plus this into this term. So as a result, you get a root 2 by under root 2 by 3 whole square. Simply I can write 2 by 3. So the probability of obtaining minus h bar by 2, the eigenvalue minus h bar by 2 is 2 by 3, and the probability of obtaining the plus h bar by 2, the eigenvalue is plus h bar by 2 is 1 by 3. So which one is the correct answer? Option D is the correct answer. So this is another question which appeared in your TIFR. The state of a quantum mechanical system in a certain basis is represented by column vector psi. An operator A corresponding to dynamical variable A is given in the same basis by the matrix A. If now a measurement of the variable is made on the system in the state psi, the probability that the result will be plus 1 is. This problem is similar to the previous problem. So here what you have to do is, first of all you have to write the you have to find the eigen values of this matrix A, that is 1 1 1 1 2 1 and 1 1 2. How will you find the eigenvalues of this matrix? There is a characteristic equation. You should find the determinant of the characteristic equation and make it 0. Then you will get three eigenvalues, lambda 1, lambda 2, lambda 3. So out of these three values, you will be getting one eigenvalue plus 1. Then you write the eigenvector. So let me call this eigenvector is psi corresponding to plus 1. So what is this eigenvector? If you know the eigenvector, then simply you can calculate, that is the probability of getting plus eigenvalue is the eigenvector, and psi, there is a whole square here, divided by psi comma the inner product psi into psi. So when you substitute all these values, you should get the answer 1 by 4. So this is a small assignment for you students. This problem is exactly similar to the previous problem. I hope you will do this one because you will get a polynomial in third degree. You have to solve that. For roots of that equation. Then you will get one root. One root will be equals to one eigenvalue. So I want to discuss another important concept, that is expectation value of an operator. So here I'll simply give the formula and I'll try to solve some numerical problems. The expectation value of an operator A with respect to some state psi is given by this expression. Expectation value of A is given by modulus psi A cap psi divided by psi psi. So this is the formula for expectation value of an operator in discrete basis. We can also write this expectation value of A bar as, this is expectation value of A, the operator. It can be written as like this: integration psi star of x into x psi of x dx divided by the normalization parameter, that is psi star x into psi of x dx. So this is for continuous basis. For example, the energy of a system is given by the expectation value of Hamiltonian h cap. So there are many questions in GATE which are related to the expectation value of Hamiltonian. Expectation value of Hamiltonian is nothing but the energy of the system. Hamiltonian is nothing but, I can write it as p square by 2m plus potential energy, right? So this is the Hamiltonian. If you want to write this Hamiltonian in operator form, this will become minus h bar square 2m del square plus this will become v of x operator. Another important formula, the expectation value of operator can also be written as the product of the eigenvalue into the probability. For example, we have a matrix. Let me call a matrix is B, and which is a 4 by 4 matrix. Okay, and I am trying to calculate the expectation value of the operator associated with the matrix. Then for this 4 by 4 matrix, you will get 4 eigenvalues: a1, a2, a3, a4. Then the total expectation value of this operator can be written as the eigenvalue, first eigenvalue a1, and the probability of obtaining eigenvalue a1 plus a2, the eigenvalue a2, multiplied by the probability of obtaining eigenvalue a2, like that, plus a3 p3 plus the final eigenvalue a4 multiplied by the probability of obtaining the eigenvalue a4. So this is the formula. This can be written as like this. So how to find expectation value of the position operator and momentum operator? For odd integral, the expectation value of position operator is 0. So these are the very important points you should remember. If the integral is odd, then the expectation value of this position operator will be 0. Next, to calculate the expectation value x, compare given wave function with the Gaussian wave function. So this is Gaussian wave function. You have to compare the given wave function with the Gaussian wave function. Then we can easily directly calculate the expectation value. For example, calculate the expectation value, the position expectation value of the wave function psi of x is equals to e power minus x square a square by e power ikx. So whatever be the given wave function, so here the given wave function is like this. So this is given wave function. Compare this wave function with the Gaussian wave function psi of c. So what is the formula for Gaussian wave function? This is exponential minus of x minus delta x minus expectation value of x whole square, and this is divided by 2 delta x whole square, the whole divided by under root 2 pi delta x whole square. Here this is expectation value of the position operator, and delta x whole square is nothing but the variance. So I can call it as the variance of the system, and delta x can be written as, delta x is the standard deviation. Delta x is the standard deviation, delta x whole square is the variance, whereas x is the expectation value here. So compare the given wave function with the Gaussian wave function. So this is the given wave function and this is the Gaussian wave function, and I'll write this given wave function as e power minus x minus 0 whole square divided by a square into e power ikx. So this is given wave function. Now compare this given wave function with the Gaussian wave function here. So from this I can say that the expectation value is 0. When you compare the both, I can write the expectation value is 0. So see here there is 0 parameter, and in the 0 place I can write delta x here, I can write expectation value x here. So simply I can write the expectation value of the operator x is 0. No need to do the calculation. What is the formula? Actual formula is, if you want to calculate expectation value, you should calculate this one, psi of x and psi of x. You have to do this one divided by psi of x into psi of x. So this is a time taking process. When you do the calculation, of course you will get the same expectation value 0, but the trick here is compare the given wave function with the Gaussian wave function, and you can from that data you can collect what is expectation value, and even you can calculate delta x also, delta x square also you can find that, you can find from the given equation. From the given wave function, a square will be equals to 2 into delta x square. If you compare both the wave function, this a square will be equals to 2 into delta a square, or I can write delta x, the variance will be equals to a square by 2. So sometimes in the exam they will ask you to calculate the variance, or in some exams they may ask what is the standard deviation. Standard deviation is delta x, that is simply a by root 2, right? So first point is, for all integral the expectation value of position is 0. For any other integral, to calculate the expectation value of x, compare the given wave function with the Gaussian wave function. So for this you have to remember this Gaussian wave function formula. The wave function of a momentum operator is given by a into e power I kx with momentum p is equal to h bar k. In the previous cluster, I have discussed that the wave function of the position operator will be a Dirac delta function, and for the momentum operator, the wave function will be a plane wave equation. For a momentum, the wave function will be a plane wave equation. For the position, the wave function will be a Dirac delta function. So the expectation value of momentum is 0 for bound state or a state with a real wave function. That means, for example, if the wave function is given by psi of x is equals to n into e power minus x squared by a square, then the expectation value of momentum is 0. For any real wave function, the expectation value of momentum is 0. For any real wave function, the expectation value is 0, whatever be the form of that wave function. If it is real wave function, the expectation value is 0. To calculate the expectation value for imaginary wave function, compare the given wave function with the plane wave equation e power ikx. For example, calculate the wave expectation value for momentum for a given wave function psi of x is equals to n into e power minus x square e power ikx. Here we have two wave functions. The first term is real term, that is n into e power minus x square a square, and the second term is e power ikx. Therefore, I will calculate the expectation value of the momentum as the expectation value of the momentum for real wave function plus the expectation value of the momentum for imaginary wave function. So expectation value of real wave function is simply 0. Then what is the value of the expectation value p for imaginary wave function? For this you have to compare the given wave function with plane wave equations e power ikx. So the first part, the expectation value is 0, and the second part is simply e power ikx. Then the expectation value is simply momentum p. Okay, or you can write this is 0 plus h bar k. So therefore, the expectation value of the given wave function psi of x is equals to n into e power minus x square a square e power ikx is simply h bar by k. So this question appeared in your CSIR exam. If the given wave function is odd, expectation value of x is 0. If the given wave function is a real wave function, the expectation value of momentum will be 0. For any other wave functions, to calculate the expectation value of x, then compare the given wave function with the Gaussian wave function. Whereas in case of momentum, to calculate the expectation value of momentum, For imaginary wave functions, you compare the given wave function with the plane wave equation e power ikx. Then it is easy to calculate the expectation values. Yes, this is a question which appeared in TIFR 2014. A particle moving in one dimension has unnormalized wave function psi of x is equals to x e power minus x square by lambda square, where lambda is real constant. The expectation value of its momentum is, first check it whether the given wave function is real or imaginary. Okay, since we are looking for the expectation value of p. First of all, you should check whether the given wave function is real or not. If it is real, the wave function will be 0. The expectation value will be 0. Since given wave function is a real wave function, there is no imaginary term, so the expectation value momentum is 0. It's simple, right? So option D is the right option. So now I want to discuss Heisenberg uncertainty relation. According to Heisenberg, it is impossible to measure a pair of canonical conjugates, for example, position and momentum, simultaneously at arbitrary accuracy. This is Heisenberg uncertainty principle statement. So mathematically, this can be written as delta x into delta p. Uncertainty in position is delta x. Uncertainty in position and uncertainty in momentum will be delta p, which is greater than or equals to h bar by 2. Uncertainty, or you can say error in x. Okay, so delta p is uncertainty in momentum, or you can say error in the value of momentum. The product of uncertainty in position and momentum will always greater than or equals to h bar by 2. We can also express the uncertainty relation in terms of energy and time, like delta E into delta T is greater than or equal to h bar by 2, and the angular momentum delta J into delta theta, theta is also greater than or equals to h bar by 2. Delta J is angular momentum and theta is angular displacement. So the product of uncertainties in theta and J is always greater than or equals to h bar by 2. So the fifth point here, it is very important. The product of uncertainty is minimum for Gaussian wave function. The product of uncertainty is minimum for Gaussian wave function. What is Gaussian wave function here? So I will write the Gaussian wave function, that is psi of g. It will be like e power minus x minus expectation value of x square by 2 into delta x whole square and divided by under root. So here also you can write 2 delta x whole square. So delta x is uncertainty. Delta p is uncertainty momentum. So that will be equals to h bar by 2. And for any other wave function, any function other than Gaussian wave function, the delta x into delta p is greater than or is greater than h bar by 2. Generally we will get this is delta x into delta px is equals to h bar. So this question appeared in Delhi University exam, Delhi University PhD entrance exam. So the product of uncertainty is minimum for Gaussian wave function, that is like this. So this is one property of Gaussian wave function. Moving on to next property, uncertainty in position can be written like this, and uncertainty in motion can be like this. Two operators A and B satisfy this relation. The product of uncertainties delta A and delta B is always greater than or equals to h bar by 2. That is one notation. And we can also write in terms of commutators, commutating operators A comma B divided by 2. For example, you can also write delta x into delta P is also greater than or equals to modulus x comma P commutator divided by 2. We can write like this. So what is x comma P? The commutator x comma P is IH bar, and this is a modulus by 2. So this can be written as modulus of I is simply 1. So I can write h bar by 2. So the uncertainty principle in terms of position and momentum, you can derive like this: delta x into delta p is greater than or equal to h bar by 2. So instead of writing h bar by 2 for any operators, two operators a comma b, I can write the uncertainty principle like this: delta a into delta b. This is more general form of uncertainty principle. Delta a into delta b is greater than or equals to expectation greater than or equals to modulus of commutator a comma b divided by 2. There is a problem. This problem appeared in just 2014. Two operators A and B share all the eigenstates. Then the least possible value of the product of uncertainties delta A into delta B is, there are two operators share all the eigenstates. The least possible value of the product of uncertainties, the minimum uncertainty state he is asking. He is asking the what is the minimum energy state. So the minimum possible value of the product of uncertainties delta A into delta B is. So please remember that the formula is, when you have two operators A and B, then the product of their uncertainties is greater than or equals to modulus of commutator A comma B and divided by 2. So what is the relation? How can you calculate this commutator A comma B? He is given that this is important statement. Share all the eigenstates. A and B have, the operator A and B have common eigenstates. They have simultaneous eigenstates. We can say that A and B will have simultaneous eigenstates. Simultaneous eigenstates. A and B have simultaneous or common eigenstates if they commute each other. If they commute each other. Commute each other means the commutator A comma B will be 0. If this happens, A comma B, commutator A comma B is 0, then A and B will have same eigenstates. They will share the all eigenstates. So that is the statement. This is one theorem. So two commutating operators share all the eigenstates. That means A comma B will be 0. Then the least possible value of the product of the uncertainties delta A into delta B is. So simply substitute here A comma B, A and B operators. So if you want, you can write the operators here also. A and B share the eigenstates, but when commutator is 0, so this is by 2, which is equals to simply greater than or equals to 0. So what is the least possible value here? So the least possible value will be 0. So option B is the right option. There is one problem which appeared in CSIR December 2012. I want to discuss this problem here. If a particle is represented by normalized wave function psi of x is equals to, a particle is represented by a normalized wave function psi of x is equals to root 15 into a square minus x square divided by 4a power 5 by 2 for minus a less than x less than a, or otherwise it is 0 for all other x values. Otherwise it is 0. So this is the wave function. This is the normal wave function given for a particle. Okay, and the uncertainty in momentum. The question is you have to calculate delta p. So this is the wave function given for a particle. Now he is asking what is delta p. You know that the given wave function is a real wave function. You can check it. There is no imaginary term. Since the given wave function psi of x is real, the expectation value of momentum p will be 0. If expectation value p is 0, what is the formula actually? The uncertainty in momentum delta p can be written as square root of expectation value of p square minus square of the expectation value. Square of the expectation value. Here the square expectation value is p. Here the expectation value of p is written like this and it's square. For given wave function, for a given real wave function, this value will be 0. Therefore, delta p is simply square root of expectation value of p square. So here you have to calculate p square, the expectation value of p square. Since the given wave function is a real wave function, the expectation value p is 0. If expectation value p is 0, it means it need not to be p square 0. So we cannot say simply expectation value of p square is 0. I don't know whether it is 0 or not. But okay, we have to check. We have to calculate the expectation value of p square. So I will start here. The psi of x is given by root 15 a square minus x square divided by 4a power 5 by 2, or else is 0. This is for minus a less than x less than a. So this is the question appeared in CSIR 2012 December. Okay, so let me calculate this p square expectation value. So what is the formula, students? Since psi is normalized, I will write the expectation value. The formula is like this: psi star of x minus ih bar dou by dou x. This is p and this is p square into psi of x dx divided by integral psi star of x into psi of x dx. So this is the formula to write the expectation value. So here we are trying to calculate expectation value of p square. So since the given wave function is normalized wave function, then this value will be equals to 1. Now I can write this as psi star of x and square of minus I. It will become minus, and this is like minus h square dou square by dou x square psi of x dx. The denominator is simply 1. Now I'll take out this constant term, that is minus h bar square integral. What is psi star? Since psi of x is a real value, psi star will be real value, and you have to differentiate psi of x 2 times. So I will write the first time derivative here. So you will get the first time derivative, and directly I'll write the second time derivative here. So it won't take much time for me. The second time derivative will give you a square minus x square into minus 2. So this is the derivative term I'll get here. So when you substitute these values here, I'll get minus h bar square and 15 is there by 16 a power 5 integral minus a to plus a. This is the range, since the wave function is a non-zero wave function within the limits minus a to plus a. So minus 15 by 16 power a, and this is like a square minus x square into minus 2 dx. So you have to differentiate the given wave function 2 times, then you will get this expression. So do the integration and substitute all these values. You will get pi 5h bar square divided by 2a square. So this is expectation value of p square. Therefore I'll write the minimum uncertainty in position. The minimum uncertainty in momentum delta p is nothing but expectation value p square minus expectation value p with a square, which is 0 actually. So here you will get expectation value p square with under root. So when you substitute all these things, you will get under root 5 by 2 h bar by a. So this is the answer. Delta p is nothing but under root 5 by 2 h bar by a. So this question appeared in 2012 CSIR net exam. Before concluding this session, I want to give 2 important hints. One thing is, from this fourth postulate, every time he is asking to calculate the probability of obtaining any one of the eigenvalues, or there is another chance to ask the expectation values of position and momentum, or expectation values of p square and x square, or the uncertainty values in x and p. So with these calculations, we can also check the Heisenberg uncertainty principle. Thank you, students. That's it for today's lecture. I hope you enjoyed the session. Please like, share, comment, subscribe to our channel. Thank you.